All right. Hello, everyone. Thanks for coming and thanks for the organization for this opportunity. I think the event is going very, very well so far. I'm very happy to hear about the breakfast, which is delicious. So I'm going to talk about PyAstro, which is my personal project, hopefully a community project soon to be. So first, a little bit of introduction about me. I'm an aerospace engineer with a passion for orbits and orbital mechanics and everything that revolves space. I'm also the chair of the Python España Association, which is kind of like the Python Software Foundation representative in Spain. So I also organize the Python conference in Spain, the PyCones, since the very first edition. So I encourage you to come to Malaga to this edition in October. Lots of sun and tapas, very good. I'm a software developer at Satellogic. It's a satellite company that is building a constellation for Earth observation. And a free software advocate, Python enthusiast, hard rock lover. Please follow me on GitHub. Don't do that on Twitter. So PyAstro is a collection of Python functions useful in astrodynamics and orbital mechanics. So it's basically a pure Python package. It's all accelerated with Numba, more on this later. It's released under a permissive license. And thanks to AstroPy, it allows you to use a very high-level features, such as using physical units and stuff like that. It features some very important astrodynamics algorithms, such as orbit propagation, boundary value problem solving, etc. And I just released the 0.9 version, the same as SoundPy, a week ago. So you just can go to the documentation. It's very cool. So a little bit of history. I released this first version in 2013. This was part of a university project. I had to glue together some MATLAB and Octave and Fortran code and to analyze some orbit around Venus. And I got it to work, but only in my computer. I guess this was probably impossible to install anywhere else. So in 2015, I replaced all the Fortran with Python plus Numba because I discovered that I could more or less get the same order of magnitude of performance. So I threw all the Fortran away, and now I'm a happy man again. And the package can be installed in Windows without you killing yourself. In 2016, I implemented a very performant boundary problem algorithm that I presented in the European Space Agency. And well, last year, it was the first time that I got affiliated into AstroPy and Open Astronomy, all of this. I participated in something that is called the Summer of Code in Space, something equivalent to the Google Summer of Code, but organized by the European Space Agency. And that was an extremely positive boost for the project because I got a student full-time working on this during the summer. And then this year, well, I'm here. I'm participating in the Google Summer of Code as well, so I will have another student. And I hope that I will expand into the industry as well, because I've been told that they are using this package in my company, but I'm not that one using it, so maybe we will change that in the future, who knows. So how does it compare to the rest of the things? One of the most famous open source packages that are in use over there for astrodynamics is called OREKit. It's a Java library. OREKit is restricted to Earth orbits, most of it, because it's more geared towards commercial applications and stuff like that, not so much for interplanetary applications. And then you have SPICE as well, that maybe some of you already know, that it's a collection of libraries that they're implemented in Fortran and C. And well, PyAstro aims to be a little bit more lightweight in general. But we try to replicate most of the functionality that you can find there, and actually I'm thinking about validating against it. So let me show a little bit of code. This is some boilerplate that I use in all the programs, and as you can see, I'm leveraging AstroPy units and AstroPy time for most of the things that I'm going to do. So the central object that you have in PyAstro is the orbit object that you can instantiate using either position and velocity vectors or using the classical orbital elements, the Keplerian elements, as we will see. So this is the easiest thing that you can do to get an orbit, and as you can see, you can just define the position and velocity, the position in kilometers, velocity in kilometers per second, and you optionally give some time, and then you have it. So you have this simple representation of the orbit with the apogee and the perigee and the inclination, etc. And if you want to do visualization, then it's just one plot call away. I implemented some very simple two-dimensional visualization that can handle, orbits in different inclination, so it projects everything into the same plane. Very handy. And also, I started using Plotly last year for 3D visualization, and I have to say that I'm very happy, because this thing that you see over there, you cannot do that with Matplotlib, because as you might know, the 3D visualization in Matplotlib is too limited to do this, because the line would appear in front of the planet, which is not correct. But Plotly is very simple to use, so I highly recommend you to check that out. And it's also interactive, so I can rotate the view and etc. The other interesting thing about PyAstro is that you can read some external data. So for instance, I'm working on reading data about near-Earth objects. So a couple of databases out there that have asteroid and comet orbits. And also thanks to AstroPy coordinates, I can read as well the planetary ephemerides from the JPL. So I have all the power that comes from there, so I can have the position and velocity of the planets at any point in time. So this is a very simple example. Using AstroPy, you first set the ephemerides to be the ones that come from JPL. If you don't have them, then it will download the files from you, so you don't have to worry about anything. And then you can define the oscillating orbit, in this case of the Earth. Or you can read the orbit of the Florence asteroid that passed near the Earth last September. I have a very interesting notebook about that in the documentation. Or you can use this DASCOM5 database that, if I recall correctly, is coming from NASA as well, where you have not only asteroids, but also comets. And in fact, for the case of the Halleys Comet and some other objects, you have different observations of it. So for instance, I'm getting the observation from 1835. Sorry. So this is an example of how can you combine all of these together. So you have a nice plot of the inner solar system, and then also the Florence asteroid, the Halleys Comet, everything with a few lines of code. You can do this in 3 dimensions as well. And you can, this is another example, you can plot all the observations from the Halleys Comet. And this is very performant. Even if the orbits are very elliptic, we are doing some interesting math over here, so this is everything smooth. And a couple of words about the algorithms. I don't want you to bore you with the details, but I'm implementing some different propagation algorithms. So not only you can predict where the object is going to be in some point in time in the future, but you can also define your own perturbation accelerations. So for instance, you can, with this thing over here, I'm simulating a low thrust device in the satellite. So I can see a spiral object, because this is going to be gaining energy over time. And you can, again, plot this in a very, very easy way. This is, again, is a 3-dimensional plot, so you can rotate the view, you can pan, you can zoom, etc. So this was a little review on what you can do with PyAstro. You can find more information in the documentation. I wanted to talk a little bit about the challenges that I found with PyAstro. And I have a couple of pet peeves here. So the first thing of all is how to validate the algorithms. And I take this thing very seriously, because I believe in reproducible science and everything, and I don't want to just implement some algorithm there in Python and have the people just trust it because it comes from me. So how can we do this in a good way? This is related to the question that I asked yesterday in one of the talks. And it's very painful to say this, but in many packages that you see out there, you see approaches like this. So you want to implement this function over here, a very simple mathematical function. And then if you want to do a unit test, then you will create some sort of function that says, OK, so I'm going to check that the function that I implemented here agrees with the result that I expect it to be. So more or less something like this. OK? There are so many wrong things with this unit test, and it's still necessary to go over this in some courses, in some audiences, but I don't have to remind you that 0.1 plus 0.2 is not equal to 0.3, but the contrary works for the following example. So apart from taking into account the nuances of floating point arithmetic, we also have to take into account that I cannot just copy and paste the formula that I implemented in my unit test, because then if I make some mistake in the formula, then I'm just copying my mistake to the unit test, and I'm not validating everything. So I need some sort of external data, right, to check that all my algorithms are correctly validated. And the other thing is that the approach that I'm following now in PyAstro is just checking that, for instance, my algorithm agrees with some external result that I found up to, I don't know, 6 decimal places or something like that. And this is good because if I introduce a regression in my code, then I'm going to notice it because the test is going to fail. But how do I notice improvements in the code? Because if I go from 6 correct decimal places to 8, then the test is still going to pass, but I'm not going to notice any difference. So I have to, I don't know, regularly check how can I do this validation in a proper way. This is still an open question, and I don't have like a good answer for it. And regarding the external data for validation, this is a short summary. Nobody cares. Those who care don't share it. Those who share do it with 1 decimal place, and this is a true story. Those who share with 16 decimal places don't describe how it was obtained. It has released the source code. And those who release the source make it impossible to compile. This is, of course, an exaggeration, but when you're, when I was doing my final master's project, doing some validation of these algorithms, I found all these sort of situations, and it's very, very frustrating. So I agree with what Mark was saying yesterday. We need more papers with results, with tables, etc. So, well, if you are more interested in my research in this validation thing, you can go over my final master's project. And if you don't have external data, okay, what about validating against some external software? Okay, so I have, I don't know, the commercial software that everybody uses in orbital mechanics is called STK, and you also have GMAT, which is an open source product, and you have SPICE, which is the NASA libraries. So, okay, the first question is whether it's validated itself. And as the source is closed, then you really don't know. You have to trust them. And it's often difficult to reproduce the same result because, for instance, if you use this STK thing, they have, of course, lots of advanced propagators to, do commercial-grade orbital mechanics problems and stuff like that. But here, I'm just validating very simple algorithms. So how can I get a commercial-grade software to reproduce a very simple situation? And this is often a bit tricky, and it's not as easy as it should be. So this is a problem, and this is one of my ongoing battles implementing PyAstro. And then the other thing is that I'm trying, apart from making a lot of fun implementing astrodynamics algorithms, I'm trying to prove a point. And my point is that Python doesn't have to be slow. But it is slow if you use, a lot of introspection and complicated things, high-level code. So you have to cover yourself from that somehow. Some algorithms cannot be easily parallelized. And even if you try to do that, then you will end up with situations like this one, where I magically implemented a function that could rotate a stream of arrays using a stream of rotation angles and blah, blah, blah. And I used this numpy.ainsum function. And then I went over that code 3 months later, and I said, I don't understand this thing. So I removed it altogether because I needed to understand this code myself if I want other people to understand them. So vectorization is tricky. And I don't know anything about Cython. Last time I tried to debug any Cython code, I had to recompile the debugger, which was not a nice experience. Maybe you have some advice on that. Comments welcome. And if you use Numba, then Numba only helps you if your Python code resembles Fortran. Like if you use arrays and very low-level constructs and stuff like that, then Numba is going to work perfectly, and I'm in love with that. But if you try to use objects or even pass a function as an argument, that was only possible since the day before yesterday with the latest release. So what I try to do is to provide like a high-level layer that uses, units. So I mean, I don't mess it up with kilometers versus meters or stuff like that. And then below, I convert everything to kilometers or some canonical unit, or I remove the units or whatever, and then I do all the number algorithms. And this is more or less working, except for the astropy.units performance sometimes, because astropy.units conversion code is very, very slow, so I had to remove this from loops. I cannot convert, I don't know, from kilometers to meters every time I want to do an iteration or a propagation or anything. So I have to remove all of this from the API, and sometimes this, this high-level nice API is not that nice or not that high level. So I'm trying to, make the most of this combination, and there's not always a clear answer. So this is still an ongoing work. I had to skip this part because I'm over time, but I just wanted to mention this sentence over here that I love from John Hunter, the creator of the Matplotlib package, and just wanted to comment that all the time that I spent building, documentation and tutorials and doing outreach and etc. has paid off a lot. And even there are many open astrodynamics libraries out there, but mine is probably the one that I spend more time building all these kind of things. So I think it's a very good experience and a very good use of your time. So you have, this is all I had to say. You can find the slides there. Please join our PyAstro chat, which is on Riot/Matrix. Thanks to Stuart Mumford for recommending that. We have a Twitter account, and I always finish my presentations with a picture of a rocket. And this time I chose a rocket that was made by the Spanish Space Agency in the 60s to reflect the humble origins of the project, but its potential. Thank you very much.
We only have time for a couple of questions, and I think the first hand I saw was...
So I'm wondering about your issue of external data, and in terms of testing and storing external data and then passing that on to your users, is that something you do, or how do you mitigate that, or is your external data just text files and it's not a big deal?
I mean, yeah, the external data that I have so far, it's very small, like, I don't know, some example that says that the velocity should be this, this, and this, so I don't have like big amounts of text data to validate against. Right now, I'm shipping the tests along the code on the pip installable packages, which is something that I've been considering about removing in the future, but sometimes it helps me, getting better issue reports. So I'm still hesitating on how to do that. But for the moment, that is not a problem. In the future, it will be a problem, definitely. So.
One more.
Very nice code. What about extrasolar system dynamics?
Well, that's a very good question, because actually what I intend to do with PyAstro all the time is to make it very general. And actually, there was some guy simulating TRAPPIST-1 with PyAstro, and of course you can do it because there's nothing in the code that is specific to the Earth, and I'm very careful about that, because for simulating, I don't know, Earth observation satellites and stuff like that, you have lots of packages, but here it's more general. So you just have to define like the attractor and what are the bodies orbiting around it, and define the orbits, and that's it. Then, if you want to, do, I don't know, an observation from the Earth to that system over there, then you have to properly use the correct reference frames, which takes me to my lightning talk yesterday. And in the same way that you can combine meters and kilometers and you don't mess it up because astropy.units takes care of it, at the moment you cannot combine an orbit in an ecliptic frame and an orbit in an equatorial frame without messing it up. So this is like my next priority for this year.
All right, let's thank our speaker again.
Thank you.